Next, we have a paper by Sheikh, Zika, Hudson, and Stream. Dynaite Class in lunar meteorite Northwest Africa 14900, mantle derived, and talk by Daniel Sheikh.
Good morning to everyone in the audience, and good morning to everybody watching online. My name is Daniel Sheikh, and today I'll be talking about preliminary work that we've been working on a recent Dynaite class found within a recently classified fragmental breccia NWA 14900. So before I start, let me just pose a question. What are lunar Dynites, and more specifically, why are they important? Well, Dynites are olivine-rich igneous rocks that comprise at least 90% olivine. And lunar Dynites in particular are pretty important because experimental modeling of forming the differentiation process of the LMO has shown that Dynites are some of the earliest formed LMO mantle cumulates and thus make up a significant portion of the lunar mantle and are thus important to study if you're trying to understand the petrological evolution of the lunar interior. Also important is that recent remote sensing data has identified some olivine-rich regions exposed on the lunar surface. So if I show this diagram right here, all of these stars represent potential olivine-rich exposures. And perhaps not all of them are, but maybe some of them could be olivine-rich mantle rocks. So this begs the question, if we have material on the surface of the moon, and could it be that we might be able to sample some of these LMO Dynites in our existing collections and existing samples that we have? When we look at the sample collection, though, it's a bit different. Dynaite clasts are actually rarely observed. Dynaite itself is a rare lithology that we don't really find too much in Apollo and lunar meteorite samples. What we do find, most of the Dynites are actually suggested to be related to MG suites, not LMO cumulates. And so the idea to form these are that these Dynites are either cumulates of the plagioclase under saturated MG suite parental melt from probably a deep crustal source, or they're residues of MG suite partial melting, also, of course, occurring in the crust. So mostly crustal Dynites more so than mantle-derived Dynites. And ultimately, it would be important to be able to identify lunar Dynites that are unequivocally mantle-derived. And so to do this, we investigated a Dynaite class within Northwest Africa 14900. Here's an image of the class. So just a bit about the methods that we did. So we conducted SEM analysis at Portland State University. We obtained BSC images. We did ES false color chemical maps of our sample. And for the probe work, we actually did it at Washington University in St. Louis. These are the probe conditions that we used. We pretty much looked at olivine, which made up most of the Dynaite class, and a bit of chromite in the class as well. We also obtained bulk rock trace element analysis of the entire sample to get a sense for what sort of class diversity we have in the sample. So here are the results. So what you're seeing on the upper right-hand screen is a BSC montage of our sample. Our Dynaite class is this dark class right here. It's the largest class we have in the sample, and it's about 2.2 millimeters in diameter. A better way of seeing this class would actually be looking at this image right here, which is a false color ES chemical mosaic of the sample. And so what you can see is that each element is mapped to a specific color. So in the case of magnesium, it's green. So of course, our Dynaite class stands out as it has the darkest color of green, and thus this is our olivine-rich sample of interest. Now, you also notice there are quite a lot of other clast lithologies present. We have some poicolytic clasts, we have basaltic clasts, we have impact melt clasts, we have a lot of anorthositic clasts, and we can see that this sample clearly is diverse in terms of the lithologies it contains. And this is supported by the trace element composition. So what we're looking at is FeO on the x-axis against thorium, samarium on the y-axis, respectively. And we can see that our sample plots somewhere in the mixing trend between feldspathic highlands terrain material, Procidum creep terrain, and Mare material. And mostly, for the most part, this is highlands material, although we do have some components of the other two in there. Now let's talk a bit about our Dynaite class. So here's our Dynaite class here. This is a BSC image of the class, and on the right, this is actually a cross-polarized image of the class. And so the class itself is angular in texture and appearance. It's fine-grained in texture, sort of has a granular, granoblastic type texture. You can see there's some 120-degree triple junctions present between some of the olivine grain boundaries. You'll notice that it is a bit difficult to get a sense for the grain size of olivine in the sample. So olivine takes up at least 99.2% volumetrically of the sample. And so we relied on the cross-polarized image to get a better sense of the grain size, which is about 110 microns for the larger grains. Chromite makes up the remainder of the sample at about 0.8 volumetric percent, and its grain size is about 20 microns. You also notice that we have this extensive network of weathering veins running through the sample. If you took a look at the binoc images earlier, you'd see that this sample is probably the most weathered of all the lunar classes we have in this sample. Now, more interestingly, when we look at the chemical composition of the olivine and the chromite, so what you're seeing here is also a false color EDS chemical mosaic, so with each element mapped to a certain color. You'll notice that the olivine itself, for the most part, is equilibrated with a forced-to-right content of 90.8 plus or minus 0.1. And it's also unzoned in both major and minor elements as you go from throughout all the different grains in the clast. One thing we were trying to do was to measure aluminum and chromium in the clast, but unfortunately, though, we couldn't measure those. So all we have are detection limits. For aluminum, we have 53 ppm, and for chromium, we have 89 ppm. This was in the olivine. Now, for the chromites that we measured, we obtained chromium numbers of about 78.9 and magnesium numbers of about 52.5. And those I'll talk a little bit about later on. Another thing we were trying to get was to get a sense of what kind of equilibration temperature this class might have experienced. And so we were hoping to get aluminum to use the aluminum and olivine geothermometer, but since we couldn't do that, we had to rely on the olivine spinel iron magnesium geothermometer. And so we used the equation from this study in 1995, which relied on a couple parameters. This is the partition coefficient of the magnesium over iron of the olivine against the iron over magnesium of the spinel, and some other inputs as well. Now, when we plugged in these values, we obtained an average equilibration temperature of about 994 degrees Celsius. And of course, the range we have, it has to do with the uncertainty with all these input parameters that I just mentioned. So that brings the question, is this temperature a magmatic temperature, or is it more of a subsolidus equilibration temperature? And to check this, we looked at a figure from Priscilla et al. 2016, which essentially what you're seeing on the x-axis is the chromium number of spinel against the partition coefficient of spinel and olivine for iron and magnesium. And this line right here from Priscilla et al. 2016 is the equilibration line for spinel at magmatic temperatures. And there's a systematic relationship between the chromium number and the partition coefficient. And so they also plotted some lunar troctolites and dynites and pallasites. And what you'll notice are that these samples plot off of the trend. And so this was suggested that these samples had underwent some sort of subsolidus reequilibration process, likely slow cooling at depth. And so when we plot our sample, we can see that it also falls along this trend, and thus likely the temperature that we obtained earlier was the subsolidus reequilibration temperature. And so if we extrapolate the value back to the line and we obtain a corrected partition coefficient that we later plug back into the equation, we obtain a temperature of about 1225 degrees Celsius, which at least gives us a lower bound estimate on our magmatic temperature. So how does our Dynaite class compare with other NWA Dynaite clasts? And one that we looked at was a Dynaite class from NWA 11421 that was discussed by Treeman and Semprich in 2019. And this Dynaite class specifically has a granoblastic texture. It has a pretty Mg-rich olivine with an Mg number of about 83.5, and it has an equilibration temperature between 900 degrees and 995 degrees, which is within range of values that we have. The difference being that this class also contains plagioclase and pyroxene, and using that, they were able to determine an equilibration pressure, which they later used to determine an average depth for where the sample might have been derived from, which they estimated at 68 kilometers of depth. And so using this, they suggested that this Dynaite clast was actually derived as a fragment from the upper part of the lunar mantle. So when we compare this with our sample, they have similar textures. The Mg number of our Dynaite class is slightly higher than this one, and they have a similar range of equilibration temperatures. So even though we can't get a census through the equilibration pressure, we can at least make inferences that there are some similarities between the two classes, so perhaps they're probably related in some way. Now, how does our Dynaite class compare with other Mg suite ultramafics, so including Mg suite dynites and troctolites? So this figure on the left is from Priscilla et al. 2016. It has the chromium number of spinel against the Mg number of olivine and the Mg number of spinel. And so what you'll see are that the troctolites and dynites from the Mg suite are these blue dots right here, and our sample is this yellow triangle right here. So at a given Mg number of olivine, our sample does tend to be on the high end compared to Mg suite lunar dynites, and it tends to plot within the Mg number of the spinel of other lunar dynites. So there are some similarities there. Although it is interesting to note that the chromium number of the spinel in this Dynaite class is noticeably higher than that of the lunar Mg suite dynites. Also important to note is this figure from Alardo 2011. This is comparing the Mg number of the olivine against the chromium in olivine. And so pretty much what you have are early magma ocean cumulates, which show from the models high abundances of chromium in the olivine, and whereas the MG suite study samples that were measured by this study showed relatively low abundances of chromium in the olivine. We couldn't detect chromium, like I said earlier, in our sample, but when we plot it on this diagram using the detection limit as sort of an upper bounds estimate, we can see that it is extremely depleted even compared to some of the MG suite Dynites, which I think the lowest one right here is about 450 to at least 500 ppm.
2 minutes.
Thank you. So we can see that they're definitely this Dynaite class is definitely similar in its force-to-right content to both LMO cumulates and to MG suite Dynites, but it's highly depleted in terms of its chromium content. So, for our conclusions, what is the clast? How did it form? Well, what we can say so far from our preliminary work is that this is one of the most primitive lunar Dynites sampled thus far, with its high olivine Mg number and its high chromium chromite number. Is it an LMO cumulate? Well, on one hand, the olivine Mg number does tend to match some of these cumulates, and it is similar to the NWA 11421 Dynite, which was inferred to be a fragment of the upper mantle. But the chromium contents in this in the olivine in this Dynaite class are too low when you compare those to the modeled concentrations of chromium in LMO cumulates from recent models. Could this Dynaite class be related to MG suite Dynites? Could it be an MG suite Dynite? And it is supported by the olivine Mg number, the Mg number of the chromite, and the fact that this sample shows a similar subsolidus cooling pattern to some of the other MG suite Dynites. However, the chromite number of the chromium number of the chromite is different from that of MG suite Dynites. It's slightly higher, and the chromium concentration in the olivine again is lower by at least a factor of 4 compared to MG suite Dynites. So could this sample maybe have experienced some impact modification that could have changed its primary characteristics? And it definitely could have. We can definitely see that the texture of it sort of has a recrystallized texture, and thus you could have some sort of impact modification that could have altered the chemistry, at least of the olivine and of the chromite, and potentially led to some of the equilibration that we see. So further work we want to do to constrain all of this is to do EBSD analysis of olivine. This gives us a good sense into the deformation of the olivine, but also into getting grain size distribution of the olivine grains, since I couldn't really get them earlier due to the fact that it's hard to see where the grain boundaries are. Also, we want to do laser ablation ICP-MS work of the olivine grains to obtain better estimates on the aluminum, chromium, and some of the compatible trace elements within olivine. So with that, I'd like to say thank you, and these are my acknowledgements.
Thank you, Daniel. We do have time for comments, questions.
Yeah, Tim Fagan, Waseda University. A nice presentation. From your introduction, it looked like many of the class and the whole rock composition was anthracite rich, yeah? But you're looking at this class, it looks like it has this affiliation with the MG suite. Are there other clasts in the breccia that look like MG suite clasts?
Great question. Thank you for that. If I can go back really quick. So yes, there are definitely MG suite clasts we have in the sample. So we have some MG suite troctolites over here. This poikilotic class is also related to MG suites. So we do so a lot of the anorthositic or Highlands material in this sample is MG suite. Yes.
Alan.
Hi there, Alan Treeman, LPI. This is a fantastic find. I'm just wonderful to see more Dynites like this. One thing that's really interesting comparing this one with the NWA 114421 that we looked at was that your chromite is actually just plain chromite. In the other sample, the chromite is all in symplectites with augite, and this weird texture that you see also in troctolites and all, which has been suggested to be some kind of metasomatic alteration. So it's really neat that you just have chromite on its own, and that's really good to see. The other sample we looked at, I don't think has very much troctolite or MG suite material in it, but this is fantastic. I'd like to urge everybody in the audience to look for Dynites. This is, to me, one of the next frontiers of lunar petrology. So thank you.
Thank you. And I absolutely agree. There are many more classified meteorites that are coming in. There are lunar meteorites that could have more Dynaite clasts for future study.
I've got a quick question. Can you show the cross-polarized view of the class again? Yeah, thank you. I can't see it real well from this angle, but it looks to me like it's not just a random pattern of interference colors. Maybe there's maybe some vestige of a coarser former grain size. 120 micron grains. awfully fine grained for something you think is from the mantle or from even a MG suite intrusion. So I can't see it too well, but I'm thinking maybe you may have vestiges of a coarser texture.
Thank you. That's definitely something that we want to look more into, and hopefully with EBSD analysis, getting a good sense of the grain size distribution, the olivine should help with that.
Thank you. I think we need to move on to the next talk.
Yeah, we do.
You can show Paul the picture later.
Okay, next we'll